Today we are going to spend a second day graphing rational equations, and we're all done today. You'll be able to graph a rational equation that looks like the one you see here, where f of x is equal to x minus a 3 over top of an x squared minus a 3x minus a 4. Today we are going to define two of the vocabulary words that we put on yesterday's notes. Now you may either go back and add them to yesterday's, or you can add them to today's. Either way, I'm okay with. So the first one is a discontinuous function. A discontinuous function is a function whose graph has one or more gaps or breaks. The second one was a continuous function. A continuous function is a function whose graph has no gaps or breaks. Today we are going to look further at graphing rational functions. Now, something I need to point out is some rational functions are not hyperbolas. Yesterday we graphed just hyperbolas. Today we're going to graph rational functions that are not hyperbolas. For example, look at this one that I've listed right here. Now, if you look at this, here's what the graph looks like. So if we go over here and kind of look at the graph, looking at the graph over here, now notice where does the graph cross the x-axis? Look right here at -2 and at +3. Now notice what would cause this function to go to 0 if I plug a 3 in there or if I plug a -2 in there. So if I want to find the zeros of the function, I would simply set the numerator here equal to 0 and solve. So our x-intercepts will be 3 and -2. Alright, now let's look at what would cause the denominator to go to 0. Okay, so look at the asymptote here. The asymptote right here looks like it crosses at where? X equals -1. Okay, now notice over here, and we did this yesterday, if I plug a -1 in there, I get 0 in the denominator. So my asymptote is x equals -1. Okay, so let's go ahead and uncover that. And there's my asymptote. So in a nutshell, if we glance at this now, you're going to see this. If I want to find where it crosses the x-axis, I set the top equal to 0, each factor of the top equal to 0, and solve for x. And if I want to find where the asymptote is, I set each factor of the denominator equal to 0 and solve. In this slide, it just puts into formal definition what I've already stated. For example, we have here f of x is equal to p of x over q of x. So this is our function. So f of x is equal to the p of x on top and the q of x on the bottom. Now p and q are polynomial functions in standard form, and they have no common factors other than 1. Okay, now if this exists, then I can say the zeros of the function is p of x, which is the numerator, set equal to 0. And of course, your vertical asymptotes is q of x, which was your denominator, set equal to 0. In your notes, let's go ahead and take a look at this one here. First of all, let's work through this one together. I want to take the function, and the first thing that I want to do is I want to factor the numerator and the denominator if possible. In this case, I can only factor the numerator. So if I factor the numerator, it becomes x plus a 4, x minus a 1, all over x plus a 3. Now, using the previous rule, I want to set each of my factors of my numerators equal to 0 and solve. So if I set this equal to 0 and solve, I'm going to get x equals -4. If I set this equal to 0 and solve, I get x equals 1. So that tells me that my zeros of my function are -4 and 1. That means it crosses the x-axis at -4 and 1. Now, as far as my asymptote, we're going to set the denominator here, x plus a 3 equal to 0 and solve, which gives me a vertical asymptote of x equals -3. Now let's go ahead and graph this a little bit. If you graph it, notice there is a t-chart here, and using this chart we took some domain values and plugged it in, and when you plug them in you're going to get values such as these. What does this do for us? Well, on a graph, after I graph the x-intercepts as here and here, and then I graph the asymptote as I graphed it here, then I want to know what the graph does around those points. And by plotting some domain values and getting the resulting range values, I can see what happens to the function, and I can see it goes in this fashion. Let's have you try this one. Go ahead and pause the video, and as you take a look at it, remember you're factoring the numerator, and then you're finding the x-intercepts and the asymptote using both the numerator and the denominator. Okay, go ahead and pause it. Now that you've worked through this problem, you looked at the top and you factored it, and you see by looking at the top it's going to factor into x plus a 6, x plus a 1, over top of x plus a 3. So I can see that if I set each of these equal to 0, set the top equal to 0, you get x equals negative 6. Take the top here equal to 0, you get x equals negative 1. So my zeros are x equals a negative 6 and a 1. And for your asymptote, set the bottom equal to 0 and you get x equals negative 3. So your asymptote, x equals negative 3. Now on the next slide, go ahead and pause it again because I want you to graph it. Now here's the graph of this function. It's going to look like this. Notice the asymptote, vertical asymptote here. And let's uncover that so you can see what the axis vertical asymptote is. X equals negative 3. And now in order to show the graph here and where it is on the coordinate plane, we plug these in so we could better see where each of the points were along the coordinate plane. In this slide we're going to begin to talk about horizontal asymptotes. Now the existence and the location of a horizontal asymptote depends on the degrees of the p of x and the q of x, the polynomials that make up the rational function. Now a special note, so in your Cornell notes make a little asterisk off to the left, and I want you to put this little note here. First of all, let me preface this statement by saying this. Remember in the previous slide I indicated that the graph cannot cross the vertical asymptote. Well, sometimes for rational functions, the graph can sometimes cross the horizontal asymptote. So put that in as an asterisk off to the left in your Cornell notes. Here is the rule for finding or determining what your horizontal asymptotes are. So I want you to write this completely down in your notes as it's shown here in this slide. Notice it says, let f of x be equal to p of x over q of x. Now, p and q are polynomial functions in standard form. Alright, so first of all, take the degree of p of x. Remember the degree, if you put it in standard form, it's the power. Okay, now, also look at the degree of q of x. If the degree of p of x is greater than the degree of q of x, there is no horizontal asymptote. Okay, let me say that again. If the degree of p of x, for example, if you have x to the second plus whatever out here, divided by, and you have a degree to the first power plus whatever out here. In this situation, if the degree of p of x is greater than the degree of q of x, there is no horizontal asymptote. Now, if the degree of p of x is less than the degree of q of x, for example, let's say that you have x plus whatever, and on the bottom you have x squared plus whatever, then that tells you that the horizontal asymptote is going to be the line y equals 0. In other words, the horizontal asymptote will be the x-axis, the line y equals 0. Now, if the degree of p of x equals the degree of q of x, so if let's say that I have x to the second plus whatever, and on the bottom, let's say that I have 2x squared plus whatever. Now, I'm going to put a 1 in front of that p of x there. Now notice the degrees are the same. See, x squared, x squared. So what's going to happen is my asymptote will be the ratio of the coefficients. So in this case here, I can see that my horizontal asymptote is going to be 1 over 2. So in this case, my horizontal asymptote is y equals 1/2. Let's take a look at 3 examples here. In the first example, notice first of all, what do I have in the numerator? Well, my p of x is x to the second, my q of x is x to the first. Right away, look at your notes and you're going to see that there is no horizontal asymptote. Okay, so that you will have no horizontal asymptote. Now, let's take a look at the top. Can I factor the top? Well, if I look at the top factors into, what does that become? Looks like it's going to become x minus 4 and x plus a 1 all over x. Now, the zeros of the function, remember I set the top equal to 0 and solve for each one of these. So my zeros of the function are going to be x equals to a 4 and x is equal to a negative 1. Now my vertical asymptote, remember we set the bottom, the q of x, equal to 0 and solve. So that means my vertical asymptote is going to be x equals, and what would cause the denominator to go to 0? Well, 0 would. So my vertical asymptote is going to be x equals 0. Now if we graph this with our graphing calculator, you're going to get something that looks like what I've shown right here. Here's what you're going to have. Okay? Now, notice your x-intercepts here and here. Now, your calculator does not show the asymptote, but you know the asymptote is going to be at x equals 0. So what you need to do on your graph is draw a dotted line at x equals 0, and then label it as well so you can see your asymptote. Also, what I'd like you to do is I want you to go ahead and put a dot showing the 2 x-intercepts so you can see the x-intercept, and then label it so it shows it at 4 and negative 1. In looking at this question, notice what you see on this one. You see a numerator that is to the first power. You see the q of x in the denominator is to the second. So, looking back at your notes, you see that p of x is less than q of x, which means your horizontal asymptote is going to be what? Well, looking at your notes, you can see it's going to be the x-axis, or y equals 0. Now, the zeros of the function, you're going to set this equal to 0 and solve, and you can see that your 0 is going to be at 2. Now, you need to factor this piece right here. So when you factor it, it's x minus 1, x plus 1, which means your 2 vertical asymptotes are going to be a positive 1 and a negative 1. This time, when you graph it with your graphing utility, you're going to see something that looks like what I've shown right here. Okay, notice I see the graph down here, and then I see the graph up here, and then I see the graph over here. Okay, so let's go and let's try to interpret that. We're going to put our vertical asymptotes in. So notice I put the vertical asymptote here in at x equals a negative 1 and at a positive 1. Remember, my horizontal asymptote was going to be at 0, and now you're just going to plot enough points over in this domain area, in between in this domain area, and over here, until you get a feel for what the graph is going to look like. Now, my suggestion is use your graphing utility to help you determine where the graph is going to be in between each of these vertical asymptotes. In this third graph, notice this time that I have first degree here, first degree to there. So these are the same. So since P of x is equal to Q of x, the degree of P of x is equal to the degree of Q of x, that tells me that my horizontal asymptote is going to be the ratio of these coefficients. Okay, so my horizontal asymptote is going to be y equals a 4. Now to find the 0, remember we set the top equal to 0 and we solve for it. So we're going to take this here, 4x minus 12 equal to 0, and solve. And when I do that, you're going to get 3. And to find the vertical asymptote, remember we're going to set our denominator here equal to 0 and solve. So I get my vertical asymptote of x equals a 1. Okay, looking at the graph of this, when you graph it with your graphing utility, it's going to look like this graph right here. But you need to interpret what that means by drawing in the vertical asymptote of, you see it right here, x equals 1, and the horizontal asymptote at 4. And then you can use your graphing utility to just kind of show what happens to the graph between those asymptotes. At this point in the video, we're going to take a little bit of a turn. There's not much left, but we're going to take a little bit of a turn. So if you wanted to pause it at this point and go get yourself something to drink and take a little bit of a break, go ahead and pause it and do so. Now that you've taken a break, let's come back and let's take a look at holes. So again, in those definitions that you had there last class period, one of them was a hole. So what is a hole? A hole is an omitted point in the graph. Now, how do you come up with holes in the graph? Well, this is how that happens. If a rational function has the same x minus b in both the numerator and the denominator, then there's going to be a hole in the graph at x equals b. Remember, as we were simplifying these, we factored the top, factored the bottom, then divided out what was common to the top and the bottom. Well, those values that you divided out, if you were to take those values that you divided out and set them equal to 0 and solve, those are the holes. Now, the only time that's not going to be the case is when x equals b happens to be your vertical asymptote. So let's take a look at an example of where this occurred. Well, first of all, looking at this question here, I'm looking and I see there's the degree of the numerator is larger than the degree of the denominator, so that means there is not a horizontal asymptote. Looking here, I can see that my vertical asymptote is going to be x equals to a 3. But before we get too far into this, I want you to notice, you can factor the top. The top is the difference of two squares. And notice here what happens. These two divide out. Because they divide out, that means that there's going to be a hole at the graph at x equals 3. Now when we graph these functions, you're going to notice that the graph is going to be the same as graphing this, the linear equation y equals x plus 3, because that's all that was left. Except the difference here, remember when we restricted the domain and you said x not equal to a 3? Well, that meant that there was a hole at x equals 3. Now the way that we show there is a hole at x equals 3 is we indicate the hole by drawing an open circle on the graph. So it shows the domain of the function is going to be any real value x not equal to a 3. So here's the graph and what it looks like. So looking at this, I can see that my graph of this line, there it is, y equals x plus 3. And I have a hole right there which I show with just an open hole. And remember that hole is there because you remember x could not equal 3. Okay, let's identify some holes in this graph. So first of all, the thing that we want to do is we take the numerator and the denominator. We're going to factor the numerator. So when you factor the numerator, you can see it's going to be x minus a 2, x plus a 3, over x minus 2. Now, when you look at that, notice what happens. This divides out with this. Now, automatically, remember, when it divides out, that means there's going to be a hole at what? X equals 2. Correct. It's going to be a hole at x equals 2. And you're left with the equation f of x is equal to x plus a 3, which means you're just going to graph this linear equation, and you're going to draw a little hole at where? Well, at this point, x equals a 2. Go ahead and pause the video, because in this slide I want you to go ahead and show the graph. And then once you've showed the graph, then we're going to look and see what you've done. Okay, now that you've graphed it, let's see if you agreed with me. Okay, here's your equation. Y equals x plus a 3. So draw it in here. And then you have x equals 2. So you're going to go to 2, and you go up to the line, and right there you're going to put an open circle indicating there's a hole in the graph at the domain value x equals 2. Okay, that's going to wrap it up for today. Your assignment next time, if you could please write this at the end of your Cornell notes. Here's your assignment. So we're going to be section 8-4, day 2, which is on page 597. We're going to be doing problems 33 through 40 and problem 45. Also, please remember to write your summary at the end of your Cornell notes. Okay, well, you have a good day, and we'll see you in class.